Hello everyone, Namaste. Today I am going to present you about mass and weight. The topic is taken from the first unit force of compulsory science for grade 10. So, I'll discuss with the mass and weight together. Quantity of matter present in our body is called mass, and the weight, the magnitude of force with which a body pulled down towards the center of the earth is called weight. The SI unit of the mass is kilogram and the SI unit of weight is Newton, as weight is a force, magnitude of force. Okay, so the unit of force is Newton. So the unit of weight is also Newton. And the mass of a pin or any particular object is constant everywhere. Because when you take a pen to a moon, of course the mass of that pen is constant. Okay? But the weight of a pin or any particular object varies from one place to another place. For example, the weight of pin on Earth's surface is more than that of the weight of that pin on the moon surface. Okay, so weight varies from place to place. The mass of the body is measured in beam balance, whereas the weight of the body is measured by spring balance. So this is the difference between the mass and weight. Also you can say it that way. Important for SE exam too. Now we have another. Now calculation of weight. How we calculate weight? We have a formula to calculate weight. If the weight of an object is W, then weight equal to the mass of that body times the acceleration due to gravity. That is W equal to m times z, where m is the mass of the body and z is the acceleration due to gravity. Okay, and W is the weight of the body. So W weight is directly proportional to the acceleration due to gravity and the mass of the object. More mass, more weight, and less mass, less weight. And similarly, the weight depends on the acceleration due to gravity. So the weight of the object at the bottoms of the mountain is more than that at the top, because the value of z at the bottom of the mountain is more and the value of z at the top of the mountain is less. So for a particular mass, if the mass is constant, then weight is directly proportional to the acceleration due to gravity. So more z, more weight, less z, less weight for a given mass. If this acceleration due to gravity is constant, that means for a particular place, different mass has a different weight. Okay, the weight of 10 kg mass at Damauli and the weight of 20 kg mass at Damauli, that different. Okay, mass having 20 kg has more weight and mass having 10 kg has less weight at the same place. Okay, so if acceleration due to gravity is constant, then weight depends on the mass of the body. Okay, so weight is directly proportional to the acceleration due to gravity if mass is constant, and weight is directly proportional to mass if g is constant. Okay, because w, weight of the body, depends on mass and acceleration due to gravity. Okay, it depends on the conditions. Okay, now we have a application of this formula. Look at here. If mass is 20 kg and g is 9.8 meter per second square, then the weight of that body having mass 20 kg equals w equal to mg, and the value of m 20 and the value of g is 9.8. So multiplying these two quantities, you get 19.6 newton, and this is the weight of the body having mass 20 kg. So it is the average value. What is the value of that body, or the weight of that body at polar regions? The value of g at polar regions is 9.83. Then the product of 9.83, what is the product of 9.83? You see it from the calculator, okay? You can see here the calculator. Okay, what is the value? 20 into 9.83, and this equals 196. Okay, that this calculation was mistake. Once more we do this. Okay, 20 times 9.8 equals 196. Sorry, this is not point here. If it is 9.83. Okay. If m is 20 kg, g is 9.8 meter per second square, then w is equal to mg, and the value is 196 newtons. Okay. So what about the weight of that object and the polar regions? It is 196.6 newton. Okay. The value changes. So similarly, what about the value? What is the value at equator? 7.8. It says 7.8. Then use a calculator to find the another value. So cancel it. 20 times 9.78. The value of g at equator is 9.7 over 195.6. Okay. The value is 195.6 newton. So we have calculated the weight of the body of mass 20 kg at different places. Okay, at the surface, okay, where the g is 9.8, it was 196 newtons, and at polar regions, when the value of g is 9.83, it is 196.6 newton, and in the equatorial regions, the value of g is 9.78 meter per second square, so the weight is 195.6 newton. So if mass is constant, then the weight depends on the acceleration due to gravity. Weight is directly proportional to the acceleration due to gravity. Okay, so this is the formula to calculate W is equal to mg. Okay, is the formula to calculate the weight. Now another. Look at it. What kilogram of mass can weight lifter lift on the Jupiter if he can lift 100 kg mass on the Earth? So We have one planets, one is Jupiter, another is Earth. So weight lifter can lift up 100 kg mass on Earth. So we start from the Earth. So what is the weight of the mass on Earth? Mass on the Earth is 100 kg and acceleration due to gravity on Earth is g1. Okay, suppose g1, you have to use the acceleration due to gravity of Jupiter also. So g1 is 9.8 meter per second square. And the acceleration due to gravity on Jupiter g2. Suppose g2 for the acceleration due to gravity of Jupiter. It is approximately 25 meter per second square. And mass of the Jupiter, okay, m2 is equal to what? We have to find that mass. Okay. So look at it. The force applied by weightlifter is considered as a constant. So the force applied by the mass by the man on the earth, it's same in Jupiter also. Okay, so we have a F1 equal to F2. So have a formula F equal to mg. We have formula F equal to mg. So we write here, we know that since we have that F equal to mg. So by these reasons, we have got F1 equal to M1 G1 and F2 equal to F2 G2. So now substitute the value of M1 G1 G2. You can find the value of mass on Jupiter. Okay, we have a solutions here. Look at here. 100 times 9.8 and 2 times 25, and by calculating we get 39.2 kg. And from this, what we see here, look at here, the weightlifter who can lift up 100 kg mass on Earth can only lift up 39.2 kg on Jupiter. Okay. Okay. Next, we have another slide on problem. Calculate the weight of the body on Moon's surface if its weight in Earth's surface. You can write here not in, on, or at. You can write at. Earth's surface is 100 newtons. So here, weight on Earth W1 equal to 100 newtons and acceleration due to gravity on Earth G1. I think you know what is the value of G1 on Earth's surface? You can write. Yes, it is 9.8 meter per second. And M1 equal to W1 G1. How it is possible? So it is because of this formula. W equal to mg. So m equal to W by G. Okay, we have calculating the mass on Earth. So we have assume for this by giving suffix 1. So the M1 equal to W1 by G1. And putting the respective values, we get 10.20. Okay, kg. So the weight, who can lift up, okay, the weight of the body when 100 Newton at Earth, the mass is, corresponding mass is 10.20 kilogram. Now, in Moon surface, the mass is remain constant, as you know that when we take plane from Earth to Moon, there's no change in mass. Okay, so the mass remains constant. So this M1 and M2 are same. Okay, in one surface M2, mass of that body is M1. So it is 10.2 kg as mass is constant. Okay. Now acceleration due to gravity of Moon is G2. Okay, equal to what the value? Do you remember? What is the value of acceleration due to gravity of Moon? It is 1.67 meter per second square. Then what we have to find? We have to find the weight. Okay, we have to find W2, weight equal to what? Okay, we have to find the W2. Let us write in the suffix notations. Oh, you can write here, look at here. So W2 equal to what? So you know that W2 equal to M2 G2. Same reasons, weight equal to M times acceleration due to gravity, mass times the acceleration due to gravity. So by putting the values G2 and M2, that is 10.20 kg. So you get the value like this. Okay, 10.20 into 1.67 equal to 7.04 Newton. So the weight of that body is 17.04 newtons on moon surface. So what we have seen, the value of weight is decreased. How much times it decreased? Let us see. Okay, how it changes. So to get that, let us divide 100 by 17.04. Okay, and this equals, I can see that, cancel it, 100 divided by 17.04 equals, how much you have seen here? 5.86 or 87. Okay, that equals 5.87 times. Okay, 5 times. Look at here. So 5.87, that is 6 times, about 6 times, approximately 6 times less. Okay, it means the weight of the body on Earth is 6 times more than the weight on moon surface. Okay, 6 times. So because the acceleration due to gravity is 6 times more on Earth than that on moon. Okay, we have alternate method for these solutions. Let us see that alternate method here. Look at the alternate method. I can use this ratio F1 is to F2 equal to G1 is to G2. That is F1 divided by F2 equal to G1 divided by G2. So putting the respective values, we get the same result, 17.0 Newton. Okay, and this is the alternate method to calculate the weight in different planets. If weight on one of the planet is given, okay, you can do this. Now we discuss about the free fall. Free fall and weightless. The falling of an object with an acceleration equal to acceleration due to gravity is called free fall. In other words, the falling of an object without any external resistance is called free fall. Okay, if there is no any external resistance, in that conditions, the falling of body is called free fall. So falling freely is known as free fall. And another is weightlessness, a condition that at which the apparent weight of an object becomes zero is called weightlessness. Okay, so during the free fall, the weight of the body appears to be zero. During free fall, the body has no weight. In other words, okay, the weight is zero. In the weight balance, when we stand, and if it is free fall, then the value is zero. Now some examples of weightlessness. In the space, the astronauts inside the spaceships experience weightlessness. Okay, the value of G is zero or approximately zero. So the weight of that astronaut seems to be zero. Okay, weightlessness. That condition is weightlessness. Similarly, we experience effects of weightlessness for a short period of time during come down in swing. in the months of when we play string, then we feel, something in our body. That is the effect of weightlessness. And during an elevator, when we coming down, we may feel the effect of weightlessness. Okay. These are some examples of weightlessness. Now we have some exercise, copy and answer the following questions. Okay, so very simple questions are there. There are simple questions. What is mass? You define. You can do this. What is weight? What are the factors that affect the weight of the body? Weight of the body at top of mountain is less than that at bottom. Why? Now, weight of the body at polar region is more than that at the equatorial regions. Why? All these questions. Okay, you can solve by taking help from the previous videos also. What kind kilogram of mass can weightlifter lift on the moon? If he can lift 100 kg mass on Earth, solve it. Calculate the weight of the body on the Jupiter surface. If its weight in Earth's surface is 100 Newton, you can solve it similarly as before. Find the weight of the body of mass 100 kg at surface of the planet of radius 1700 km. And the mass is 6 times 10 to the rise to the power 24 kg. Okay, you copy and try to solve. Okay, thank you for watching the video. I've developed 3 parts for the unit course. Part 1, part 2, part 3. You can see all the part to complete the lesson of first unit. Okay, thank you once again.